We now take a look at logarithmic functions. Now, previously we established the derivative of any exponential function, and now what we want to do is determine what the derivative of their inverse functions are, right? And those functions are logarithmic functions. Now, just as a quick reminder, sometimes you get the question like, what exactly is a logarithm? Well, really, a logarithm is just an alternative way of expressing something that is exponential, right? So for instance, if we have a to the b is equal to c, right? So like if I know that if I take my number a, raise it to some power b, and then I'll get another number c, then it turns out this exponential equation can be converted to a logarithmic equation in the following way. With a base of a, this is saying if I take the logarithm of this number c in base a, that will give me b, right? So basically, when you look at this form of the equation, the logarithm is actually the exponent to which the base should be raised in order to get this as an answer, right? So in other words, when you say, like, what is the log of c in base a, it's asking you to what power should a be raised in order to get c. So for instance, and that's why you can have simple expressions like, what is the log of 8 in base 2? Well, because 2 to the third power is 8, then the log of 8 in base 2 is 3. Just as another example, what is the log of 0.01 in base 10? Well, what power would I have to raise 10 to in order to get 0.01? Well, that would have to be -2, right? So that's really what a logarithm is. It's saying what number should I raise my base to in order to get this number, right? Now, so that's really just the logarithm as an alternative way of writing an exponential, right? But now, since we have exponential functions, it makes sense that we should also have logarithmic functions. So let's write down the general definition of a logarithmic function. So a logarithmic function is one of the form, right? And it's like this, it's y equals, so we kind of take this form and say, okay, yes, it's going to be the log, and we're going to work in base a, and then this is where we put our variable, right? And this is how we typically write a log function in a particular base, and it turns out the restriction on the base is exactly the same as the restriction in our exponential functions. And you might remember the restriction is you can't have a negative base and your base cannot be equal to 1, right? So those restrictions that apply to exponential functions also apply to logarithmic functions, again because of this direct relationship between them. All right? So our goal is to be able to differentiate these functions, right? And what we're going to do is start with arguably the most important logarithmic function, and that's the one where our base is the number e. So just like how we can argue that e to the x is the most important exponential function, then we can also say that comparably the log where our base is base e is the most important base, right? So let's start with we can break this up into cases. Let's look at case 1 where our a or base is equal to e, which is our special number e. Now, when that happens, right, of course we could write it like this. We could have our little e there, and this would be, again, our function. But we have a nice short hand notation for this. And it's pretty widely accepted. It's on pretty much every scientific calculator. So whenever your logarithm is in base e, we refer to it as the natural logarithm, and then it's denoted ln of x, right? So our goal is to be able to find the derivative of the natural log of x. And it turns out once I know the derivative of this function, using a change of base formula, right, that's comparable to the one that we used for exponential functions, will allow us to find the derivative of any logarithmic function, right? Okay, so let's say this. So if y is equal to the ln of x, right? Well, I just said over here, right, that every exponential equation can be written as a logarithmic equation. Then it should make sense that every logarithmic equation should be can be written as an exponential equation. So this is an equation that represents logs. So if I were to, for instance, do this, right? If I took e, which is my base, and raise that to the e to the power y, and do the same on this side, e to the natural log of x, because these are inverse functions, what I have now is I have that x is equal to e to the y, right? So therefore, e to the y is equal to x. Now, why is this helpful? Well, two things. One, we know how to differentiate the exponential function, right? So the derivative of e, I'll just say e, is known, right? But the thing is, the e that we know how to differentiate is actually e to the x. Here we have e to the y. But second, we also know how to differentiate implicitly. So we know how to differentiate equations where it's not in the explicit form, like where the dependent variable is not isolated, right? So the other fact that we can make use of is that we can differentiate implicitly, and that's what we have right here. So we're going to combine these two things that we know how to do, right, and figure out what dy dx is of this, right? And since dy dx is, oh, well, let's say it this way. If we can find the derivative of this this equation with respect to x, then since there's a direct relationship between our logarithmic function and our exponential function, then we would know what the derivative of the natural log is, right? So we're going to try to figure out what dy dx is, but we're going to do it implicitly. All right, so let's see what the process looks like. Now remember, one way that we can start our implicit differentiation process is wherever there's the dependent variable y, just replace it with y of x, right? And then differentiate term by term. So that's what we're going to do. We're going to differentiate term by term with respect to x. So in fact, let me actually write that down. We are going to take the derivative with respect to x of this exponential function, so e to the yx, and then that means I have to also differentiate the right-hand side, again with respect to x. But here I need the chain rule, because I don't have my basic e to the x. What I have is e raised to another function. So by the chain rule, I'm going to get back e to the y of x, but then I have to multiply by the derivative of the inner function, which is dy dx, and then that's equal to, well, the derivative of x with respect to x is 1. All right? So once we have this, let's go ahead and rewrite it without the y of x. Right? Again, this was just a little reminder to ourselves that if we're differentiating a function of y, but with respect to x, we always have to use the chain rule, right? So let's rewrite this. So we'll have e to the y times dy dx is equal to 1. And now I can isolate dy dx rather easily. I will have that dy dx is equal to 1 over e to the y. Interesting, right? But look at what e to the y is, right? What if we wanted our answer in terms of x? E to the y is equal to x. So if I take this x and replace the e to the y, I would have found a rather simple derivative for my natural log of x function. So this is 1 over x, right? So in summary, what do we have? Pretty nice result. So we have if y is equal to the natural log of x, then its derivative is 1 over x. Right? So you could say, now it's not quite as easy as the derivative of e to the x, but it's certainly not the most complicated derivative that we've seen up to this point, right? So now we can differentiate this logarithmic function. Now, before we move on to the next, this function here we know has a domain that is, we say, restricted, right? You know, we know that the domain of the natural log of x function are all values of x greater than 0, right? All real values of x greater than or 0, greater than 0. So let's write that down. So we know that the domain of y equals the natural log of x is the set of all values of x such that x is greater than 0, right? Well, the thing is, we know, for instance, we can never take the natural log of 0, but sometimes we use the absolute value to extend the domain of the natural log function, right? So, if you think about it, if we were to, let's say, want to be able to take logarithms of any real number except 0, right? We could first take the absolute value of the x and then the natural log, right? So oftentimes, right, we extend the domain, right, of our, I'll just put it in quotes, or ln, by doing the following, right? So what we do is we say, well, we're going to let y be equal to the log, ln, the natural log, of the absolute value of x, right? Now, if we do this, then suddenly the domain switches from only positive real numbers to all non-zero real numbers, right? So now, this function, so I'll say with a domain of all values of x such that x is not equal to 0, right? we will never be able to take the natural log of 0, right? But if, for instance, we were to compose our basic natural log function with our absolute value function, right? Then we could, in some sense, extend the domain of the ln. Like we would be able to evaluate this function for more values of x than this function, right? Now, and I use the word more loosely, right? Because they're all this set and this set. They both have infinitely many numbers, right? So now the question is, if I were to take the absolute value of x, how would that affect the derivative, right? Well, let's think about what the absolute value function does, right? So recall the absolute value of x is defined by this. It's a piecewise function. If your x is greater than or equal to 0, then the absolute value doesn't change your x. That's why, for instance, if you take the absolute value of 5, you get back 5. If you take the absolute value of 0, you get back 0, right? If, however, you take the absolute value of a negative number, right? So if your x is negative, then what the absolute value does, it actually changes that sign by putting a negative in front of that. So whatever your x is, it would take the negative of that negative value of x, and that's how it produces positive numbers, right? Right. So this is actually the formal piecewise definition of your absolute value function. So then our question is, could we utilize this and think about what this composite would look like and see what its derivative would be, right? Let's see what the derivative of this function would be, keeping in mind this piecewise definition of the absolute value of x. So what this means is then let me write it like this, so my natural log of the absolute value of x, and a lot of times we drop the extra parentheses here because we have the absolute values already around the x. So this can be written also in piecewise form, right? So if our x is greater than or equal to 0, then this just simplifies to the natural log of x, right? If our x is negative, then what will happen is we'll have this, the absolute value of negative x, and that will happen whenever x is less than 0. So like these are now these two functions. Whenever your x is, well, technically, actually, let me take off the equal sign because that might send the wrong message. We know we can't take the natural log of 0, so let me remove that, right? So when my x is strictly positive, this is the function that we will use. When my x is negative, this is the function I will use. And actually, if you were to graph this function, this is what it would look like. This function actually is an even function, so it's going to be symmetric with respect to the y-axis. Okay. On the positive side, we will have the familiar looking ln function that looks like this, with that vertical asymptote along the y-axis. Now, if I have this extension to the ln, it turns out this piece just gets mirrored across the y-axis. So it's like that. Yeah, and that's what happens, right? And so if you have, for instance, a graphing utility, or if you use a website that can produce fairly high quality graphs, go ahead and plot this function, and you'll see something that looks like this, right? So it actually makes sense. I know it looks strange to have a negative sign there, but you only use that negative sign when your x's are negative. So essentially, those two negative signs will result in a positive quantity in the parentheses, right? So then the question is, what is the derivative of this function, right? Well, we proved the derivative of this, right, is 1 over x. So the question is, what is the derivative of negative the natural log of x? But what we can do is we can use our chain rule to figure it out, right? So by the chain rule, right, because now we have a composite, because we don't have an x inside the parentheses. What we have is a negative x. So by the chain rule, the derivative of the natural log of negative x, right? Well, look at what the chain rule says. The chain rule says take the derivative of the outer function, which we now know is 1 over. So it's going to have to be 1 over, and then you keep the inner function, so there's a negative x there, right? So it's the reciprocal now of negative x, but then the chain rule says I have to multiply by the derivative of what's inside. Well, the derivative of negative x is a negative 1. So what happens is I have these two negative signs, and it actually makes my derivative positive 1 over x, right? So it turns out, quite interestingly, that even when we do this extension, so if we take the natural logarithm of the absolute value of x, the derivative of this piece, which is 1 over x, is the same as the derivative of this piece, and this is what we just proved, right? So in general, so here is kind of what this whole little tangent, no pun intended, shows. It says if our function is now the natural log of the absolute value of x, then the derivative is still 1 over x, right? So then dy dx is still 1 over x, and now we can say that this is valid for all values of x not equal to 0, right? So this is an important sort of extension to the logarithmic function, and it's a useful result that even if we have absolute values around the x, the derivative is the same as what we proved earlier. All right. Okay, so that's the ln case. Now what happens if we have a different base, right? So before I write that down, here is a important result from algebra, and it's called the change of base formula. Now, if you recall, when we were working with exponential functions, we used a change of base for exponential functions, and there is a similar change of base for logarithmic functions, and this is what I'm about to write down. So if you have to find the log of a quantity in base A, so let's say the log of B in base A, and suppose you're using a calculator that only has two bases on it. Maybe they have base 10, which is called the common logarithm, and then maybe it has base E, which is what we call the natural logarithm. But what if you have to compute something like, the log of 5 in base 7, right? Basically asking you this question: to what power should 7 be raised in order to get a 5? Well, most basic scientific calculators, or even some fancy graphing calculators, don't allow you to work in a base like base 7, or like in computer science. You use base 2 a lot, right? Because of the whole binary thing that they love so much, right? What if you had to compute something like this, like the log of 80 in base 2, and you don't have base 2 on your calculator? Well, what you can do is you can change from base 7 or base 2, and you can convert it to the most commonly used base, which is your natural logarithm, your base e. And this is what it looks like. To change this to base e, you take the natural log of the quantity that you're trying to find and then divide it by the natural log of the base that you were working in, right? So this could be any base here, and now this is our standard or our natural base e, right? So with this simple formula, I can now convert any logarithmic function to the natural logarithmic function. And hence, since I know how to differentiate my natural log function, I will be able to differentiate any logarithmic function, right? So if y is equal to the log of x, but now let's write base a, right? So basically, in fact, let me erase this for a second. So now we're going to look at the case where the base is anything positive, right? So we're now looking at our second case, case 2, and that's the case when a is greater than 0, not equal to 1. So it doesn't have to be e, it can be any base. Well, just use this result. Just use this change of base formula and switch this logarithm in base a to a logarithm in base e. So using this same formula, the only difference is now I have my variable x. So the x is now playing the role of b. So this looks like the natural log of x, which I now know how to differentiate, divided by the natural log of a. And the thing to remember is that the natural log of a is a constant. Right? So the ln of a is just a constant. Right? Now why does that help? Well, the thing is, this is just, if the natural log of a is just a constant, right, and I can write it like this, 1 over the ln of a times the ln of x, then I can just use my constant multiple rule, right? Because I know how to differentiate the natural log function. We just did that. That's that 1 over x. So therefore, I can find the derivative of this function, and it looks like this. So dy dx is equal to, so looking at this expression now, bring down that constant, which is your 1 over the natural log of a, and then multiply by the derivative of the natural log of x, which is 1 over x. Multiplying these two fractions gives me the rule that the derivative now of any logarithmic function is 1 over the natural log of a times x. Right? And again, keep telling yourself that this natural log of a is a constant. All right? So now we can differentiate, in theory, any logarithmic function. And it also holds that if you try to extend this one by putting absolute values around it, the derivative still is 1 over the natural log of a times x. And it all comes because of the piecewise definition of the absolute value and with the chain rule, right? So lots of little results being utilized here. So I think it's probably worthwhile to kind of list there are 4 major results here. Let's list them like this, maybe in the form of a table. So let's say here's our function, and we're just going to write down its derivative. Okay. So if our function is the natural log of x, its derivative is 1 over x. And this is valid. So let's write this. So let's say not just domain, but let's say domain of differentiability. So in other words, for what values of x does the function and the derivative hold? Okay, so let's call this the domain of differentiability. Well, this function we know is defined for all values of x greater than 0, and so is this, right? So the domain of differentiability for this function is x greater than 0. If we extend it and put absolute values around it, it turns out that the derivative is the same, right? This was one of our second proofs earlier. Now, but the difference is this function has a domain, and like this function as well, of where x cannot be 0, right? Can be negative, can be positive, can't be 0. We'll never be able to take the natural log of 0. But at least we could say that this domain just, it seems bigger than this one, right? Okay, and then now let's state the results. So what if we have a general logarithmic function? So the log of x in base a, that's this result. Its derivative is 1 over the natural log of a times x. And again, this is also valid for x greater than 0. And it turns out if we put absolute values around it, so like this, and this is also its derivative, 1 over the natural log of a times x. And again, this one is valid for all values of x not equal to 0, right? So, I mean, there are 4 results, right? But they all have, these two obviously have the same form for the derivative, and these two have the same form. So really, they're like two results in terms of the derivatives that are associated with logarithmic functions. It's either 1 over x for the basic natural log, or 1 over ln of a times x, and that's for the more general logarithms. All right. So that was a lot of algebra, a lot of stuff to derive, but now we can differentiate a lot more functions. So let's just wrap up with a few examples to see how this works. Right? So let's say we have a function that is, let's say, the sine of 3x times the natural log of x, right? And we want to find its derivative. So dy dx. Well, let's see. We have a product, so definitely the product rule. And we have a composite right here with the sine function, so definitely the chain rule. So it's going to be a combination of those two rules. So let's start out by saying what the product rule says. Take the derivative of the first function, and that is 3 cosine of 3x times the second function, so that's my natural log of x, and then plus the first, the sine of 3x, and then multiply by the derivative of the natural log, which we just proved is 1 over x, right? And that's the derivative. Now, one thing that is sometimes helpful is to take this fraction and write it as I should say the sum of these two fractions, right? And write it as a single fraction with a common denominator. And in this case, we can use a common denominator of x. So in order to get a denominator of x here, I need to multiply the first fraction, the top and the bottom, by x. Right? So then we end up getting, and I mean we can put the x in front here, so we will have 3x cosine of 3x times the natural log of x plus, and then this one already has a denominator of x, So that numerator stays the same. So then it's the sine of 3x, right? And that's the derivative of this function, all right? All right, let's try another example. So let's say we have y equals the log. Now let's say we are in base 8, but instead of just having an x, what if we have another function inside? Let's say like a quadratic, like 3x squared minus x plus 10. Right? Let's say we have this function, and we have to find its derivative. This is another composite because we're taking the log of not just x, but this entire quadratic in base 8. Right? So we can use the chain rule. Now, let's use the first version of the chain rule so you can see it clearly what happens. Right? So we're going to let u be the 3x squared minus x plus 10. Right, so let u be equal to 3x squared minus x plus 10. That means my y equation can be written as the log of u in base 8. And now I can differentiate both of these. This is our standard, power sum difference rule application. So du dx is 6x minus 1. And now we get to use our new rule for the derivative of a log function, in this case base 8. So dy du, and that's that 1 over. So it's 1 over the natural log of my base, so ln of 8 times u, right? So if I now apply the chain rule and says, well, if I want to find the derivative of this function with respect to x, I'm going to multiply these two derivatives. So therefore, dy dx is equal to dy du times du dx. Right? Now, dy du is this reciprocal. So it's 1 over the natural log of 8 times u. And then that's times the quantity 6x minus 1. Right? I'll put that over 1. So now I can actually multiply the numerator, and then in the denominator, remember we want our final answer to be in terms of x. So what I can do is replace this u with 3x squared minus x plus 10. So that is going to go right here, right? And technically it's another composite because what we're doing is instead of just taking the reciprocal of u, we're going to end up taking the reciprocal of the entire 3x squared minus x plus 10, right? So here is our final derivative of this function. So dy dx is we have the 6x minus 1 in the numerator, and then it's all over the natural log of 8 times the quantity, and I have to make sure that I'm going to multiply the entire u, which is our quadratic, 3x squared minus x plus 10. Right? Let me extend the line there. So that's the derivative of this function. And it turns out if I had absolute values around it, it would be exactly the same, right? Just in fact, speaking of the absolute values, let's do one last example. And let's say, for instance, what if we had our function be just the natural log of the absolute value of something simple like 3x plus 1. This is another composite. Let's see if we could use the second version of the chain rule and not have to write down the u like I did right here, right? And basically, this is how you could say it out. We could say it in words for the the logarithmic function, with or without the absolute value. The derivative of the natural log is going to be the reciprocal of what's inside. So it's 1 over the 3x plus 1, right? And that's the first part of the chain rule. I know it looks a little bit different because of this reciprocal, but you're taking the reciprocal and you're keeping the 3x plus 1. So you're taking the reciprocal of 3x plus 1, but then the chain rule says I have to multiply by the derivative of what's inside. So we have 3, and I can put that over 1 and get this final answer, 3 over 3x plus 1. Don't be tempted to try to reduce this, because the 3 might be a factor here, it might be a factor here, but it's not a factor here. So we would have to be able to factor out a 3 in the denominator in order to reduce this fraction, right? So there are a few examples followed up by the explanation as to why the derivative of the natural log function, or any type of log function for that matter, is what it is. And so now we're continuing to expand our library of functions that we can differentiate. And I feel like we're getting close. I feel like we're almost there. So to see what's left, why don't you tune into the next video? See you then.